last presentation of the 2 days, and I'd like to introduce you to Mark Burry. Mark Burry is one of those kind of itinerant characters of architecture. I've heard of him, of his work, first of all, at the Sagrada Familia since 1979. And he's one of those figures that, as I travel around the world, either his physical presence or his work, I always seem to encounter wherever I go. So please welcome Mark Burry.
Thank you, Michael, and thank you, Michael and Achim, for organising the event. I'm lucky last. Where I come from, Australia is known as Poets' Day, which stands for Piss Off Early, Tomorrow's Saturday. So I'm very impressed that you're last in the distance. What I intended to do was describe my composition for today as being messy. And the reason I thought it was messy is because it seems to be a lot of overlapping agendas. One of the principal overlaps is the role of the architect and the role of the engineer. Another overlap is how is it for students, and how is it for professionals, and how is it for academic researchers. Another overlap was going to be history and the contemporary, the natural and the artificial, but most critically the overlap between intuition and intention. Of course, I realise that these overlaps, which I was going to describe as being messy, are in fact moire patterns, which I can't think of a better term, because it's the disturbance that these often competing agendas offer that really drives one. I did have a sort of a plan, which was to put a proposition up based on a personal position, which is looking beyond the algorithm, seeking differentiated structures through alternative computational and haptic design processes. I was assuming that we'd be seeing a lot of whoopee, here's the answer, because there has been a rash of that, particularly among some of the students I engage with, that looking at natural systems finally will give us the ultimate solution. And so I've just said that seeking the optimum solution in architectural structural design can be predicated on physical performance, but an emphasis on aesthetic judgment for trapping the stopping point can override more practical alternatives. Relying on algorithms alone, using recursive computational procedures to home in on the ideal solution may only be part of a more sophisticated design process. And the strategies I'm going to cover very quickly, that they're not going to be specifically about the strategies, they're just going to be components of the what I hope is going to be a 40-minute presentation. They include animation, something which you may have heard of, but I haven't seen today, unless I was not paying attention, which is evolutionary structural optimization. But I think that was a Freudian. That's a Freudian slip of profound dimensions. Parametric design without the animation, and hands-on analog experimentation. And of course, one of the other the other frisson we've been hearing today, I think, is the role of the model. Should it exist, or has its time gone? And the proposition is that conceptual engagement and human judgment on issues such as division of labour in the selection of differentiated structural design options sit above reliance on computational rigour per se. I hope that's provocative, but we're not going to have any time to be stoked. But that's possibly what was my proposition, that we still put ourselves above the machine, whatever the machine yields. I thought I would deal with the division of labour by taking on a sort of brief excursion of what floats my boat, or when my boat was first floated on the natural scene. So here's a bit of nature. Now, I actually, in the paper that's almost finished, the organiser will be pleased to hear, talk about a treehouse as being my first engagement with natural systems. I had permission from an unwilling parent to build a treehouse in a large mature apple tree, provided I didn't actually engage with the tree in any sort of physical way. So I was allowed to use rope to fasten the platform to it. And there's anybody in the room who, maybe you're all too cool to do tree houses, but I wasn't. But the tree house presents a particular problem of trying to get a flat surface in an object that doesn't really want to have a flat surface inserted in it. And that's when I remember I must have been about 9 or so, became aware of the difference between branches and trunks, and the difference between small branches and big branches, as I was trying to find appropriate fastening points. But that was kind of like an awakening. But the real time it hit me was when I was in I had my last 2 years at school, and I was school in England, so I did A-levels, and I had a terrible time because I had chosen people who knew better than me had chosen sciences for me, so I was doing physics, biology and chemistry. But I managed to wangle in an art A-level by stealth, and I also managed to do some mathematics for the first year. Now, the odd thing about doing biology where I studied was that we didn't actually study it previously. We just went straight into the A-level without having any previous experience. And I ended up having this really thrilling experience looking through microscopes and all this stuff that possibly others had enjoyed for years before. And I will never forget the revelation that this simple organism called moss, I don't know if anyone knows about moss, hopefully nobody knows about moss because the slides should be very informative, but this is what moss looks like when you're close up. Any of you have lain on the side of a riverbank, a moist riverbank, and found yourself just an inch or so from moss, like this one here or here, might have noticed these tiny little hairs that stick out of it with little blobs on the end. And the more inquiry you give, you sort of, what are these blobs? And it turns out that they've all got fantastic names, but they're obviously the spore heads. I mean, they're the size of a fraction of a pinhead. I mean, they really are just like hairs, but when you look at them very closely, they have a lot to say. And these little things here, which I'm not sure if they're kind of contemporary or historical, but they look like diaphragms, because it's exactly what they are. They're called a perculum. And the perculum is a little kind of membrane with a ring round it. And when the weather gets to just the right temperature for the spores to do their dispersal, the ring tightens like a sphincter and the thing pops off, revealing these things here. And these got a very odd name too. I'm afraid it's something like 31 years ago, so or more. A perculum sticks, but I never remember the name of these things. But these things are little fronds which are hygroscopic. And if it's humid and the spores are going to just fall uselessly to the ground below, then they close up. But if it's nice and dry, they open up and the wind carries the spores away. That's about as far as my nature lesson will go, but I really want to just make the point that this idea of division of labour, we've been talking about differentiation of structure, but I think I've been trying to look at this up, but my understanding is that it's what I knew as division of labour. Basically you differentiate because something is doing something different from the other. Of course there's decorative differentiation. You might say this part needs to be more attractive in a decorative sense than the other, but generally differentiation is the division of labour for organisms to be able to do their thing. And we started off looking at an amoeba which only had one cell and had limited prospects for division of labour, but at least it had something called a vacuole, I seem to remember. But then we moved on to Hydra, which were cellular organisms with very, very, very uncomplicated, and then straight into the world of radiolaria and things you could only see in the microscope, which were just fantastically complicated. Now, I'm going to be using Gaudi as the vehicle for my excursion. These are these drawings, by the way, of how it all works. I'll see all of these today. So I thought to go from this to this would be an appropriate shock for the end of a long day, second of two. This is the nave roof of the Sagrada Familia church. Those of you who heard me talk about just over a month ago will see some material again, but I'm going to be talking about it in a completely different light, I hope. And I promised you, those of you who were here last time, that I would talk about these columns tonight. It's quite clear that Gaudi conceived this part of the building as a forest or a wood, and that these columns would be supporting a canopy. The building is atypical in that not only was it only about 5% finished when Gaudi himself died aged 74, but he'd worked on it for 43 years. He worked on it for 43 years before he had to sign off. And he had at least modelled the building at a scale of 1 to 25 and 1 to 10 and to at least allow the successors to have a go at completing it. So my role in the building since 1979 for the first 20 years, and that sounds pretty odd, doesn't it? The first 20 years was actually trying to untangle the geometries, and we will look at this column in a minute, this particular column of 8, and try and understand a little bit more about its description. An act of investigation that probably would only have resulted, given the work that it required, through the need to build it. And I'm reasonably confident if they weren't trying to finish the building, then a lot of the stuff that we'll look at now would never have been in our attention. Now, this model, which I talked about last time, and we've heard referenced many, many times today, won't need any more description, other than to say that it's the first example of an interactive model that I'm aware of. And as I said last time when I was here, it, I think, should put a flag up for anybody who gets very excited about so-called interactive models today, as if that's entirely a contemporary phenomenon. Because what Gaudi had done was inverted the loading of the building so that the building was, this representation of the building, which is through scaled bags of birdshot linked with strings, was mirroring in reverse what he expected to happen in compression. And I think this is a truism that needs further investigation. We've started looking at whether something that takes a shape in tension is in fact the same in tension and compression, and it looks like there might be some slight differences, but you'll just have to watch the space. But the point is that he had a process for experimentation. He completely subverted the paradigm of plan, section and elevation for representation. I mentioned last time that the way forwards from this aspect was to put the sailcloth inside, photograph it, turn the photograph the right way up, and paint over it. And that's the design process. And it's a design process that took him 8 years to perfect, and it went on, this is the interior, and another 6 years to extract the information from the hanging model, which is a scale of 1 to 10 on site. And 6 years later, in other words, after a total of 14 years of pretty intense activity, he was able to complete at least the basement, or the crypt of the church. And so this is the first bit of nature to look at, both in the sense that the building is a building which nature has affected through gravity, its actual physical condition and description, firstly. And secondly, these columns, which are very different from the one I just showed you in the nave of the Sagrada Familia, are in fact naturally occurring stone. There is no carving to the stone. It's a hexagonal prism of basalt, similar to the Giant's Causeway in Northern Ireland. The idea of the builder and the architect being intimately involved with each other was never true in this building. Apparently Gaudi felt that these naturally occurring basalt prisms were overstructured and required some adjustment from the stonemason, who nevertheless insisted that Gaudi stood next to the column while he did this as a gesture of faith. Now, what I didn't talk about last time, which is the most crucial thing about this building and one of the most crucial problems, which again I have not really seen commented on, despite it being pretty obvious when you think about it. The general term for this kind of, my understanding is, the general term for this kind of structural experimentation is to yield an equilibrated model, and it's called equilibrated because basically all the lines of forces are directed axially down the connecting tissue, as it were. So, for instance, all these columns are inclined because we know where the forces are coming from, because the model assumed that shape when it was hanging upside down. But presumably, when you've got a building as complicated as the one that we saw hanging upside down, it's only equilibrated when it's completed. And if it's semi-complete, perhaps it isn't the shape. I mean, the idea would be obviously to take that model. I know it took 8 years to make, but in the interest of science, with a pair of garden shears, just to hone off the top or bottom, depending which way you look at it, 2/3, and see what happened to the rest. But my suspicion from the simple experiments we've conducted are that the model would reform. So the fact that the building was abandoned after 14 years of just a crypt completed on the basis of cost and other issues means that we actually have an unequilibrated building. But if you look closely here, you'll see that isn't an issue, because he had thoughtfully provided these about an inch thick, 2 centimetre thick layers of lead in between the stone. So not only is it an interactive model, but it's actually an interactive building. So we assume, sorry, that's a royal we, I assume, not having seen this written anywhere yet, that he presumed that the building would actually relax into its final form once it was completed. So that's the first bit of nature. Now we're going to move on to the second experiment in structural design, which is the columns for the Sagrada Familia. Now I'm going to look particularly at this column and this bifurcation at the top here. These columns are all, they've all got numbers. This is the column of 6 and this is the column of 8. And so that's the column of 6 and this is the column of 8 here. And the intriguing thing is the fact that it's got this very smooth profile at the bottom, which slowly evolves or devolves into a Doric profile. So about the middle of the column, about here, you can see it's just got this purely Doric profile, and then it forms these creases in ever greater profusion until at the top it's almost a circle. My sadistic tendency's gone, but when I was a bit more pugnacious, I'd ask students to stare moodily at one of these columns for as long as I could have a long coffee break and try and work out what was going on. And everybody assumed it was some kind of weird morphing, some sort of extrusion. But of course, to make the columns, we need to really understand what's going on, because it's obviously not an accident, and we do have the surviving fragments of model. The theory is this. Gaudi used 3 ruled surfaces. We looked at 2 last time I was here. This is the third, the helicoid. And the ruled surfaces, or second-order surfaces, are characterized by the fact that their double curvature is nevertheless arranged through straight lines. So you can take any number of straight lines on the surface and define the surface through that. So a helicoid typically is a staircase. Now in this photograph here on the left-hand side you can see the column. This is a contemporary photograph that was taken in the 20s before he died, so it's no fudging, it's fact. The left-hand side is the column that for a long time he envisaged as being the columns for the Sagrada Familia. And we know about trees having their sort of helicoidal movement. I gather it's through the gravitational pull of the rotation of the Earth. And we know that in the Renaissance, quite often building columns were Salomonic and curving. But apparently he came to the conclusion quite late in the piece that they were too unidirectional and he needed to actually try something more subtle. And that's when he came up with the idea of this column here. And it's the relationship between these two which are not apparent. But what in fact we're looking at here is the intersection of a column twisted, in this case, anti-clockwise, with exactly the same column twisted clockwise. So in your mind's eye, if you can put those 2 columns together and say, what is the resultant, what is the result of the interaction between those columns, then you can see the genesis of this column. We also heard a little bit about engineers and architects testing things. I thought this would just amuse. This is actually Gaudi's homemade testing device for the strength of masonry. It is vaguely absurd when you look at the mass that's on this beam here, and it's got this rod coming down that's obviously designed to, in some way, break this little sample of stone. So he wasn't a person that flew by the seat of his pants, as it may often seem. He really knew his stuff. And he knew his stuff because he did it himself. Now here's the genesis of the profile. Briefly, it's a convex and a concave parabola, which helpfully meet cotangently when they come together. And they have some parameters which describe them, none of which we're going to move on to today. So this is what the profile looks like at ground level. And the best way to look at this column, I think, is through introducing the 4th dimension to it. And we can see that in this animation here. What is happening is that, in fact, there's not one profile, but 2. And these 2 profiles are counter-rotating. each of those profiles is the barley sugar twist. I can show you what that looks like when you put them both together. But if you say we're only interested in the material, which is the grey area between the profiles, then that is the source of these creases. As the profiles counter-rotate, these creases become more exaggerated. Now this is where the nature thing comes in. What happens if you continue this particular algorithm, shall we call it, upwards? Well, obviously the column will go back the way it came. And so what happens, in fact, is we find that just as we thought we had one profile at the bottom, there were two. At this point, we find that there are actually 4 profiles, not 2. And hence, we now have 4 profiles counter-rotating. And when we get to that point, it obviously go back on itself. We find obviously that these 4 profiles are actually 8, which are counter-rotating. So there's sort of serial growth being implied here that leads to the description of these columns. The profile itself is simply discovered. It's just a whole series of straight lines forming those 2 parabolas, concave and convex. And if I just move on a bit, you can see. So that's the source of the tree-like base to the column, and you can see in the way that this forms the sort of the Doric fluting as the column rises, eventually, like all of Gaudi's columns, eventuating in something approximating a circle. This image here, you can see there's the extent or the subtlety of this move. It's not a very twisted barley sugar at all. It's just a slight twist of 22.5 degrees to the right, to the left. That's what they look like when they're together, and that's what the resultant intersection is. So that's the union, and that's the intersection. Now this applies for most of the columns in the building. If we move on to this column here, where we get the branching occurring, that's what it looks like. And we haven't got time for me to ask you to pause for thought and work out what is the arrangement. It's the same schema. It's 2 counter-rotating forms. So I'll say that this tree, which is photographed just outside the Sagrada Familia, is the clue for the approach to this whole bifurcation. What this object is a simple downward counter-rotation of an oblong down to this point here where they become a square, where they're exactly out of sync, out of phase by 90 degrees. So there's the alpha form, there's the beta form. This is what they look like when they're together, and that's the resultant form. So those of you who have got time on your hands, hours of fun taking any form you like, superimposing it and counter-rotating it and seeing what comes out. But it's actually very difficult to guess, I think, that the result of this move is going to give you something as subtle as that. And that's the point which is joined by at each 4 corners, the same thing's happening with squares. 2 squares are counter-rotating. Alpha, beta, that's the intersection. Sorry, that's the union, and that's the intersection. So you can go from the square to the octagon to the 16-sided to 32, approximating on to the circle, which is where it meets the ceiling forms. Well, that's the Gaudi pre-1926. I thought I would go back over what we're doing now, which doesn't have immediate material from him other than a drawing. So this is looking at the completion of the Passion facade on the west side of the building. When Gaudi died, he'd managed to complete the apse and just most of the Nativity facade. He'd completely modelled this area here and the sacristies at a scale of 1 to 10 and 1 to 25. The sacristies are the prototype for all the remaining towers, and that is why there's confidence among the successors that there's enough material to continue in good faith. After he died, the Passion facade was continued more or less a copy of the Nativity facade. In fact, it's extremely contemporary because whereas these are circular in plan, these are elliptical, and the idea for the main front is that the larger, the major axis for the lips will become the diameter of these towers here. This is what it looked like when I joined the building in 1979. They had finished literally the year before the second transept, and this actually is taken in about 1985 when they started building the nave at last. So when I arrived, they'd just finished this. And those of you who read the Robert Hughes book from 1992 to come out with the Olympics will have read this very erudite tome that ends with about 40 pages of diatribe against the work of Subarax, who's the sculptor who was given the chance to interpret Gaudi's drawing, which I'm about to show you, and complete this facade. When Subarax was caned by Hughes, he'd only halfway through completing the facade, this lower part of the facade, but worse still, there's actually no reference that I can recall from Hughes that recognised that the facade itself was only half built, and that in fact there's the top half. The work that I've been doing with colleagues in Australia has been the completion of this. It's the project of which we only have this one drawing to go from. It's not even the drawing, it's the photograph of the drawing. And you can see from here that there's a reasonably faithful interpretation of the fabric of the building, but if you actually look at the sculptural groups, then it's actually quite hard to you can see that there are some similarities, but Christ is up here, whereas in there we are. There's Christ on the cross here, whereas Subarax has put him up hanging rather painfully from a horizontal steel cross. So the way we've taken this forward is to look at these as bone-like objects. Here's a couple of bones, some more nature. The reason that apart from the fact they look like bones, I sort of feel that this top half of the facade ought to be reflecting the actual business of hanging from a horizontal cross. And so what I'm going to show you is a use of these particular geometries that Gaudi was specialising in the last 12 years. He didn't use any other geometry than these ruled surfaces, and try and somehow get a fusion between a rigorous geometrical outcome in terms of the description that he himself was applying to the building, and this more subtle need to express the passion of Christ. So as usual, we start with the sketch, and the sketch then leads to a description of a condition whereby we've got these two surfaces which both have straight lines associated with them, and we want those straight lines to coincide. And the difficulty we have here, and why it gets very mathematical, is that if we know where P2 and P3 are, we need to calculate where P1 is. This form, by the way, that you're looking at here is like a cooling tower form. So it's as you can see from the straight lines on the surface, it can be described by straight lines. This is the hyperbolic paraboloid, which always has these straight lines at its edges, the directrices. So the idea is to get these two lines to coincide. Similarly, if we know the point 1, can we find point 2 and point 3? So this leads to a completely different form of description for the building than that which we're used to. And we're looking at something called the schema, or the diagram that's used to communicate between the architect and the computer programmers and mathematicians who are actually going to give us the information that's going to yield these mathematical outcomes. And so that's the schema here. It's explaining that there's a couple of hyperbola. All the things you see here are parameters with values that are flexible. And that's as close as we get to having a drawing for this particular part of the building. This meant we go straight into scripting columns that look like this. And this is the prototype made from wax, the rapid prototype that we first experimented with 4 years ago. And then that information ultimately drives the parametric model. Now, of course, we have no idea what Gaudi would have done with the computer, but the way we treat the computer in the office is that it has to do more than simply be a way to do the job more quickly. We have to do something with the computer that would extend the work in some way. And what happens in this parametric model is that every single dimension, every single line is connected in some way with each other. You can't make an adjustment to anything in this model without it affecting the whole of the construction. For instance, I hope you can't see it because it's meant to be subtle, but there's a 10% increase in the gap between each column. So this gap here is 10% bigger than this one. And this whole arrangement has to conform to a finite given dimension. Okay, so we might want to make that 10% 12%. It still has to be exactly the same width. The hexagons above have to coincide, you'll see it later on, it has to coincide. One hexagon has to sit exactly on top of each column, and each hexagon has to have each of its edges kissing. But you can obviously work out if the columns are changing their intercolumnation distance, then obviously the hexagons themselves are all subtly growing, each by a fraction of 10% as it goes up. And so does this decorative treatment on the top, all derived, I might add, from that drawing, but we can contest whether the interpretation is a good one or not. So that's the parametric model, and that is an extremely subtle use of that sort of software, I believe. It's also problematic in the sense that each of these columns twists slightly. So not only are they inclined, this one's effectively vertical, but the one over here is inclined slightly, and the inclination changes, but they also incline inwards. This one has got a pronounced incline inwards, and they straighten up as they go up. And the idea there is to get some kind of rib cage. Their actual plan is based on a parabola, so they're curved. So obviously any little thing you do, everything has to reform. And the problem is that if you make a change, often the geometry actually slips out of line. Two things that used to intersect no longer intersect, which means that the program stalls and you actually have to intervene. And I think this is hilarious because although it only takes a matter of minutes for the model to reform itself, it's now taking some hours to reform all the lost or corrupted intersections. So I sort of feel that the human touch is still there, very present, despite the sophistication of the software we're using. Because of the polemical nature of the project, we had to produce some prototypes at one-to-one. So it's back to this idea of modelling. That I've, of course, meant to make the point that it wasn't enough just to do the computer image. There was a need to actually have the wax prototypes at 1 to 10 and 1 to 25. Then after that, there was a need to get the columns up in prototypes, not in stone. So there's the wax prototype. Again, another subtlety you might notice is that the straight line of one of these hyperbolic paraboloids has to slide along the straight line of the next one. The relationship between these hyperbolic paraboloids depends on the nature of the hyperboloid of evolution, which is the other form that's going, the cooling tower form. So if you make the cooling tower fatter at the bottom, then it obviously opens up these the dimensions across here, which of course means that this all has to change. So I think that's our effort to try and challenge the computer and the associated software to do something which you couldn't possibly do very easily by hand. So here's the first of the prototypes. I believe the challenge is to look at this and say, the geometry comes second, but the physical appearance comes first. I've tried this on lots of people who don't know what we're doing, and they're very surprised to find this actually has such a rigorous, again another Freudian slip, such a rigorous a schema behind it. And there's 3 columns in place. They're there now. They've been there for a year and a half. There isn't quite a guest book yet asking for comments, but they're certainly looking for comments, and those that they've had so far have been favourable. And here are the hexagons on the top. They don't quite fit, as you can see. They're being fitted. And that's from a side view. And this is I think, another one of these moire effects. Here's the kind of condition of the Sagrada Familia, which is very messy, but extremely vital as an indication of what I believe is the way we should be looking at our working environments. I don't mean physically the working environment, the way we work with each other. And that is not to be too up a tree in terms of the digital. There's Subarax, the artist, who we have to collaborate with on every project. At the beginning, we don't tell him what to decorate. We listen to what he wants to do and then work out how we're going to conform with his wishes. So those are his tools here. Mr. Bonnet is the architect director, aged 81, as he's proud to tell everybody he meets. He works with a slide rule, which is always in that pocket and on paper and pencil, and typically, apart from the initial sketches on a sketchbook, I myself will be working digitally. This is the other sort of messy thing that part of the team, it doesn't actually work or live in Barcelona, but lives in Melbourne, Australia. So we've been very early adopters on this kind of technology. Interesting that we both have to print the model at each side of the globe so that when we have our video conferences, we're handling the same object. I'm sure social scientists would have a lot to say about that. And then ultimately, the most intriguing aspect of this, which we've also heard quite a few times today, is the need to work with the people building the building at the beginning, not at the end. And one of the great things about the Sagrada Familia is that it is a paradigm where the builders do build. There is no such thing as a contractor on the project. There's a whole series of specialists, some of whom are in-house, some of whom come in to do particular jobs, but they all work under the Clerk of Works. And the Clerk of Works is an essential part of the team, is at every meeting that we have of any importance. So then this conversation here is about how this guy, who's an nth generation stonemason, is going to make this. So the next challenge is, if we're going to use machinery to make the column, which is what he's going to do, what can we do with his machines that can't be done by hand? Is there something we can do with the granite that this column is going to be made from, which can't be done by hand? And that's what we're there to look at. Basically, we want these hyperbolic paraboloids to be as thin and edgy as possible to try and do this expression thing. Now, he's quite interesting because not only is he from a long line of stonemasons, but he's also a bit of a whiz. He at computing, so he's a computer programmer himself. And Chris Williams before was talking, I think, very pointedly about the need to get under the bonnet. And I can't help but agree. And the fact that this guy here has taken the trouble to learn how to program this machine here. Not only has he programmed this 5-axis machine taken straight from the car industry to do its thing, but he's also added another couple of axes through a turntable. So he's actually got 7 axes of movement. And originally he didn't like me showing this picture because he said he was worried about his competitors. Now he's realised that even if his competitors get this machine, they won't know what to do with it. So we're able to look at it. And finally, just to show the way the columns are lined up, there's the drawing and there's the columns behind it. So you can see it's a pretty good match. How are we doing for time? Another 10 minutes maybe? I thought I'd take you into the... Just start leaving when you've had enough. I know I would. What's very interesting is taking this into the next dimension, which is working with the innovative structures group, who are our colleagues at RMIT University, and their evolutionary structural optimization software. And what the software does is it will take a notional mass and just whittle it away, testing it for efficacy to a point like that, where you can see something emerging. This is what's known as a design space. So we're looking at a mass front on, and it's representing part of the colonnade. And there's a condition which is saying that the top and the bottom are separated, but they're connected by what are going to be 3 columns. So when you go through this, I find this is magical myself, this process. What emerges, and there's no bullshit here, this is a group of engineers who we work with simply taking the facts and seeing, and I think you can see the interesting similarity between what Gaudi had drawn, you can remember the drawing, and what emerges. Of course, you take it all the way, as sometimes engineers do. No dig there, particularly, but you would get this, which isn't quite the same thing. So we might have lost one there. What this is about is taking the schema. So this is the engineer schema rather than the geometrical schema that I showed you. This is the way our structural engineering colleagues have looked at the problem. So you can see that it's physically recognizable. It's given some constraints by the fact that these columns will be inclined. But these ones, there aren't any constraints. And then you can see the inclination. And this is a whole series of these whittling away, and you get something which isn't too far from what. It takes ages, this process. It's many, many hours of computing. I think this one is 36 hours to do what I'm doing. It has to check every little cube to see whether it's really necessary or not. And we do have an animation of this, which does show how this all looks. Now, as we know, Gaudi didn't have these tools, but it's obviously the intuition was transcendent if he was able to produce something which the latest computational techniques verify but don't actually create. Right. This is looking at the structural optimization at work. I first became aware of it when I saw this series of 2D exercises from Mike Z and his team. And what it's doing is looking at, if you take a mass and you have it supported from one point, what would its ideal shape be? And this is what it emerges. So this is the kind of nature connection that actually a cherry and an apple are actually ideally shaped to do the task that they have. And equally, this is what happens if you have something which is hanging between two things. Now, it gets very interesting now because it used to be called ESO, now it's called BISO, bidirectional evolutionary structural optimization software. The reason it's interesting for me is because I asked Mike, everything seemed very reductive. What happens if you actually start adding stuff? And so what he's done here is a series of experiments where he's looking at, in this case, adding material to form this arch, in this case subtracting. So if you subtract from an oblong, you get this shape, and if you subtract from this triangle, you get this shape, and if you add to a notional plane, you get this shape. And apparently they have exactly the same performance physically and in all other respects, except they don't look the same. You get these kind of very weird and unbuildable, at the moment, objects like this. But this is the most interesting of all the images, because this is the reductive process starting with this, and this is what you get. It's the ideal table to take a mass of whatever it is there. And this is where you take a design space and say, make me a table that would support this weight. And they're similar but not the same. But apparently the similarities from an engineering point of view are fantastic. Like they're very, very close, volume, centroids, all sorts of things. I said to Mike, but Mike, they don't look the same. He said, yes, you're right. Doesn't matter. Now, of course, I thought that was the most telling opportunity for our dialogue to go up a notch. It does matter, of course. And of course, what it's now opened is a whole debate with we do a lot of work together. We have several Australian Research Council grants looking exactly at this whole dialogue issue between architects and engineers. And now, of course, it means that we now know that there are obviously lots of optimal solutions. You would have thought by definition there should only be one, but apparently there's lots. I mean, here's an example of this. Again, I think this is a very good, because it messes things up a bit, and we still make a choice. The architect will choose one rather than the other, probably. We have taken this stuff on. This is work in progress. It's a competition that we got into the final group for a monument, a New Zealand War Memorial in Hyde Park, I think, and working with an artist who conceived of a albatross winging its way back to New Zealand, suspended between two crossing arches that would look a bit like this. So we started looking at whether we could actually make this into something approximating the structure of a hand, where these are the bones, with something intentional along the top. And this is the original sketch that we were working with. And here you can see the beginnings of a model which can be sculpted. Now, the only interesting thing about this stage, because I say it was work interrupted by not having won the competition, but we are slowly taking it forward, is looking at this work where we're actually seeking to combine a parametric model, this ESO software, and finite element analysis. So what this is doing, it doesn't show anything, but it's actually looking at whether or not you can get the required movement, because this is meant to be a vaguely kinetic object, and still maintain the physical properties. There's obviously the sort of stress diagram there. Now this work's been taken up by Dominic Holzer, who has just finished his master's looking at this very thing. He's been trying to look at this relationship between architecture and civil engineering via the two research. We run a laboratory, and we're a laboratory rather than a studio because it implies that there's experimentation. And Mike runs the Innovative Structures group. And Dominic has found himself in the middle doing his master's, having been in practice. He was an associate at Allsops for a few years. And he's just trying to deal with this. So he did a series of projects looking at we're looking at is Hugh Whitehead will know about this. He's sort of, I think, coined the term of co-rationalization. Does it come from Hugh if he's in the audience? But anyway, the idea of actually the architect and the engineer designing in tandem, which has been talked about today a bit. And this is a screen for the Beijing Biennale, which we were contributing to 2 years ago, and was done. And this was very interesting because what it revealed was that the engineers in their experimentation weren't able to yield results in time to influence the project. So this was kind of another messy thing, that if you're experimenting, sometimes experimentation period is longer than the time you actually need. Dominic's been looking at using this software to find what would be the ideal form for a tower, again using the constraints from the engineers, and a whole series of outcomes. But the one that I just wanted to dwell on is this issue here, where he's actually looking at the analysis of the task sequence and duration and the number of softwares that you actually require. So in this case, the workflow diagram showing the original relationship with the various software we all have to do. So you can show this tower being whittled away as if it's such a simple press a button and you've got a tower, but in fact it's a very clumsy association of all this software. And so his work's been looking at a whole series of plugins which will allow eventually a containment of all this process. We still seem to be a very long way off getting this kind of conversation. Now this isn't a question of just whether one software will read the three-dimensional output of another software. It's actually more fundamental. It's actually looking for the performance characteristics that are associated with each model and trying to find a way of getting those performance characteristics to interrelate. Moving on to the scruffiness of a student, this is Stephen Swain, who wanted to look at using Mathematica as a design tool. And he's experimented in, this isn't Stephen Swain's work, just as I noticed, isn't it? He's been looking at using Mathematica, and he's a senior student doing the pre-major. Pre-major isn't the final project, it's just the experimentation you do to try and state your case. And he's worked hand in hand with an engineering student at the final year. So this is, I'm just going to flash through it. It's just an amazing opportunity that we didn't think would come quite this far, when you've got the abilities of an engineer being able to be harnessed with the abilities of the architect to take something far forward. Both the individuals said they had never expected to get where they got to. An interesting thing about Stephen was that he had actually failed the course previously. So in many ways he didn't look as if he'd be the right student to take this on. But he got into this stuff very eagerly. This is the sort of equations that the engineer Stephen would describe what he'd like to do, and the engineer colleague would find a mathematical formulae that could go into Mathematica, and between them they could work out on a number of strategies. They looked at the tower. They looked at trying to get a hybrid, there's a railway station, then a hybrid form where the inside of the surface would be one building and the outside of the surface would be another. So this is one of these periodic surfaces. What we're looking at here is a block of apartments that's containing a church inside. And so you get this kind of space on the inside and this stuff on the outside. Love to go over this project in detail, as I would with the next one, which is this bridge. But what I just wanted to draw the attention to was the fact that there is this very fertile engagement that can only happen if you've got these cross-disciplinary opportunities. And the trouble with schools of architecture typically, the ones that I know of, which are quite a few now, where there is a school of engineering round the corner, like I was at Cambridge University and we only had to step outside and there was the engineering school, the only reason we ever went in there was to break something. We never engaged with them in any way. And it doesn't matter where I go, with the exception of Bath, I have not come across any really sensible programs. I'll be interested to see how Bath's, if it's continuing with the same momentum, but certainly it's been very, very difficult in Australia to get engineering schools and architecture schools. But this, from our point of view, I mean, it's not a project, it's just an experiment with a particular approach to design and a particular way of coordinating work with architects and engineers. Now let's get into the home straight and get back to Gaudi. So this all seems highly contemporary, I hope, because I want to try and dash it all by showing that in fact this kind of thinking was there with Gaudi a long time before any of this computational stuff came along. And so we're back to nature again, looking at this door in Casa Bayo. The question about depth, by the way, was solved by Gaudi in the lighting the depth by just simply putting dark blue tiles at the top of the tower and white tiles at the bottom and a gradation between the two, thereby not having to worry about having a all-nighter space at the bottom. Anyway, that's an aside. Here's the door in the same building. What has always fascinated me about Gaudi's work is this whole sense of movement. It doesn't matter what materials he's using, they're all inert, whether they were previously living or not. Somehow he's able to get a sense of life within the material. In this case, we can see something inside that wood just desperate to get out. It's so desperate that it's already beginning to rupture in these little buds. I thought I had a detail of it, but they're beautiful little buds. It's a sort of a bit like my moss, the perculum. The perculum's gone, the little thingies are opening up, and the spores are about to come out. So that's one aspect of Gaudi. Another thing that we've mentioned today is this idea of the pursuit of perfection. And Gaudi, we would have thought with this extraordinary, rigorous approach to using geometry for the first time in his work in the last 12 years of his life, would be not particularly interested in having models extracted from the street to pose as one of Herod's soldiers with 6 toes. But Matamala apparently came to Gaudi and said, I've got this character which I think is ideal, he's ugly enough to be one of Herod's soldiers, but unfortunately part of his physical status is he has 6 toes. So should I just make him with 5 toes? And Gaudi apparently said, no, of course, we must represent nature and all its foibles. Okay, that might seem a bit of a one-liner, but we'll keep this one going. This is the lantern above the doorway that connects the cloister of the Sagrada Familia with the main towers that Gaudi built, the nativity facade. So there it is, it's the rosary doorway, and on either side there is a arch springing from some figures on both sides. On this side you can see this strange thing. This is 1896, by the way, just to give you some more messiness. I think it's very contemporary. It's a fish that's morphing into a head. Okay, I think it's very contemporary. And the fish is holding a bag of gold and it's tempting this young virgin into prostitution, apparently. There she is there, looking up skyward, asking for help, or this monster. On the other side, there's another monster doing its thing with man, a young man. And this young man is being tempted by this creature here, which seems to be a salamander, which morphs into a, see it better here, into a head here. Before we go on to the actual figure, the interesting thing here is that if we were talking about this in 1896, we'd say that Gaudi had stretched the head. But interesting now, if we were talking about this, we'd say, oh yes, he's got some non-uniform scaling going on. But the point is that this is an extraordinary contemporary thing to be doing. Not only that, the actual subject matter, again it's on the topic of monsterism that I'm dwelling, is what this creature's handing to this guy is a bomb. Because in 1896 there'd been a rash of incidents where anarchists would rush into the opera house in Barcelona, second only to La Scala in size and pomp and splendour, and chuck in a grenade and then run for cover. And this apparently was very upsetting from the patron's point of view, but certainly an example of terrorism, which, if we take the recent rhetoric, is something which is only of our age. But I just think, here's this 1896 sculpture. Okay, so where's this all going? Well, where this is going is an understanding, I hope, an understanding, not the understanding, of what these little motifs are around the outside of this window. Now, I'd love to spend more time explaining the ruled surface geometry here, and I know last time I did talk about these lines of intersection being fourth order curves, three-dimensional curves, where these surfaces intersect. This point here is an intersection between three lines of intersection. Just the rigour of it means that this window, even though it was smashed, fragments of it combined with the surviving photograph meant that it could be reconstructed within fractions of centimetres from the 1 to 10 model. When it came to doing something about these little motifs here, I had a conversation with my colleagues on site, and I said, what do you think? And they said, well, they just look like free-form decorative motifs. We'll just draw them. And I said, but there's nothing on this window that's drawable. Why would we suddenly find ourselves drawing something here when the rest of the window isn't drawable? It's done by modelling, which is something which I talked about last time. So they said, oh, well, you can pursue it if you want, but it could just be that it's motifs. So I did pursue it and realised that this object here, this one here, and this one here are the same object. So the morphogenesis and the morphing that was going on in the sculpture down below is being repeated in spirit in these figures here. It's as if there's a gravitational effect from the ellipse that's pulling these out of shape, because all these surfaces here are defined by straight lines that are lying on the surface. And similarly, if you look, so that's what we're calling the alpha. If you look at the beta, this one and this one, we find exactly the same things happening. They're the same objects. They're what we call paramorphs, basically objects with the same topology but different topography. And we saw Michael talking about this, I think, in your lecture too. Okay, so we now define that there's an alpha and a beta, but what is running them? Is there an algorithm that they're associated with? And I think the answer is that there is. And that parent figure is a pyramid. Now this starts getting a little bit complicated, particularly this late at night, but effectively the alpha and the beta are morphing to each other by conforming to a pyramid. So if you can just see the pyramid there, which is this dashed line. So if you look at the base of the pyramid, that's the centre of the pyramid at the base, a point on the alpha called A is migrating to A dash. So we can see that here. There's a point here that's migrating to the edge of the pyramid. You can even see the basis of the pyramid here. That's why I'm confident it's based on a pyramid. And B is going up the edge of the pyramid to B dash, and C, which lies in the face of the pyramid for the blue alpha, is popping down to C dash here. Now, this might resonate, or it might seem like far-fetched, so maybe we have to take it a little bit further by looking at what this means physically. So on the top left-hand corner, we're looking at the ring of these objects, alpha, beta, around the outside, and down at the bottom right, we're looking at the opposite, beta, alpha, and we're looking at 7 iterations from one to the other across this. So if we look at the center one, of course, we're looking at a stage where both the alpha and the beta have been emasculated into some neutral form which has the same characteristics. They're effectively flattened out. Taking this to the next level, well, don't we have to see this to appreciate it? And I think you do. Here is in the 4 dimensions, I meant, that you need to sort of get this in the 4th dimension. Here is this sort of relaxing from the alpha to the beta. And you can see it just settling into, there it is in the neutral state, and it's homing in from this pyramid to this beta form. Now, if you think back to the door with the expression of life within the timber, I think what Gaudi's doing here is exactly the same thing with the stonework. And that, of course, this isn't happening, but in the stone, this is what's trapped. Now, the reason I'm particularly confident of this is that there is an extract from a commentary by one of Gaudi's assistants called Martinet, who asked Gaudi, said, "Master, why do you make your work so difficult? There's nobody's going to ever understand it." And Gaudi said, "But that's exactly the reason." So what I think is very important about this is the fact that such a simple little thing as these motifs are actually do have an algorithm. You need to actually tackle that algorithm to do the animation. Obviously, there's 250 frames to that animation. I didn't model every single frame individually. I wrote a little script, and it was a script that was less than 1 page long that was able to write all the different iterations. Of course, by having the script and being a kind of inquiring sort of person, I realized that, but of course, there's the stopping point. With Gaudi, he must have actually had a sense of what the ideal shape would be for the alpha and what the ideal shape would be for the beta. But what happens if you stimulate it with a bit of drugs or something and actually said it's sort of a sort of turbo alpha and a turbo beta? What you can see here is this monsterism actually appearing. It's constrained by the fact that you've got this alpha and beta in the actual finished product. But the algorithm which actually goes from the alpha to the beta can start ahead of schedule and finish after schedule. And of course, in our contemporary world, we don't actually need to even worry about what material it is. We can actually go sort of hyper alpha in glass and then just take this down for a series of iterations. This is usually better with no light at all. And you get these gorgeous, I think they're gorgeous things. It's just the same algorithm. All that's happened is that it's starting a bit earlier and finishing a bit later and coming out with this stuff. And then for those, this business of a plea for not necessarily having to get engaged with the most expensive software in the most expensive way. This is an interpretation. It's part of a piece that I'm doing with a sound artist. I'm not playing the sound now, but looking at whether this whole adventure can be explained in more poetic terms as a means to try and just answer that question that Martinet would ask to Gaudi, but what if nobody understands what's going on? So that's the penultimate thing. I'm going to finish up with, I'm going to go back to the column of 8 and make my main point, but I won't have to do much. I just need to show you it. Column generating device. Gaudi didn't have the computer to have the four-dimensional explanation of the column. He had to do it another way, so he came up with a device. Although there is some suggestion that even this device was invented after he died. The fact is, when I came to the building and had to start looking at the geometry of these columns, the guys who made the column said, well, you can worry about the maths if you want to, but in fact, it's just simply this. It's just the profile at the bottom, counter-rotating along one rail and then doing the same thing along the other rail. And you can see this in detail. It's rockin'. Okay, now I've seen a very competent individual who isn't an architect see just what I've just shown you, and he still didn't understand what this is all about. So fortunately, on another occasion, he was able to see the whole process as I videoed it. And there's the column itself doing its thing, as you can see. It's just exquisite. And here's the process. There's the profile for one of the columns, and there's Josep, he's just about to become the head modellist, getting it ready to produce one of these columns. And the way he's going to do that is put plaster of Paris. There's the guy there really trying to get to grips of what this is all about. He's actually, Carlos, he actually runs all the financing of the project. So he's kind of super bright. Anyway, so there's Giuseppe. This is a bit like watching paint dry. It takes 3.5 minutes, but I think it might ruin the effect if I do my usual scraping through it. So you can see some pretty obvious things. That's what plaster looks like when you're pouring it onto half a drain pipe. Yes, maybe I should move it a bit forwards. Oh, no. Yeah, it's building up. So 20 minutes for plaster to dry, and now we get the first of the alpha move. We're going just one way round, and you can see that what's coming out is basically a stick of barley sugar. And going back, nice and smooth, and then he's going to do it in the other direction. So now it's interfering with part of what it's already laid down, and that's how these creases start to emerge. Now, the reason I'm playing this rather than just showing you the key moments is I think, from my experience of 20-something years in, looks like it's stopped itself, doesn't it? In this game, that to lose this activity would be a real tragedy. And it's very interesting that with the work that we're doing with engineers in Australia, one of the research projects is looking at the role of the physical model as the principal device for architects and engineers to try and understand each other. So just that, even at the end of this process, Carl, as the accountant, still didn't understand spatially what was happening. He just thought it was a miracle. Even though he saw it, he just thought it was a miracle that this thing came out, and he actually watched it. But I think that the idea that that the model itself, the physical model, is the principal tool for communication between two very different professional groups who are obviously, as Gaudi himself showed, completely aligned, is a very, very interesting trajectory. And probably the computer model itself won't be enough. I'll leave it there. Thanks very much.
Thank you, Mark, for a very fascinating talk. I think as it's been a long 2 days and we're quite late, we will adjourn now. There will be a reception downstairs for all the people who participated over the last 2 days.
Yes, Achim and Mike will take our guests down. I just have to quickly meet with the promo unit for a few minutes.